So the purpose of this exercise is to discover how you can use vectors to describe lines in plane as well as in spaces. Now, let's make sure first to understand the situation. We are looking at the laser that moves along a straight line, it's the black line here, at a constant speed. And we know that at time 0, the laser is at the point A. And 1 second later, it has moved a certain distance, and it is now at the position B. That's what we know. The goal is to describe now the position of the laser, let's call it B, after t seconds. Yeah? So we want a general expression for that. Now, first thing we are going to do is let's look at the position for a couple of different values for t. So let's start with the value t equals 0. We know that at t equals 0, we are just at the position A. So the position at 0 is just the position vector to A, so OA. Now, what happens if we let 1 second pass, so at t equals 1? Now at this time, well, the laser has moved forward and is now at the position OA, so the starting position, plus 1 times AB. So it's at the new position 8, 4, which is denoted by the vector B that points from 0, so from the origin, to B. Now let's look at t equals 2. So what's the position of the laser after 2 seconds? Now the position after 2 seconds is just OA plus now 2 times AB, right? So it's 2 times AB, and we are at the position then 13, 7, so which is again this resulting green vector OA plus 2 times AB. So you already see there's a general pattern here that gives us, from which we can derive the position after t seconds. You see we always have the same starting position here, and we have the same direction vector. The only difference is that we multiply it with a different factor depending on the time that has passed. So in general, the general formula for the position of the laser is OA plus t times AB, right? So it's in the component form 3, 1, vector 3, 1 plus t times 5, 3. Okay, and that's the general formula that tells us the position of the vector of the laser after t seconds. This means that if we want to know the position of the laser after, let's say, 0.75 seconds, all we have to do is we plug in 0.75 as our t value, and we get the position of the laser, which is this, in this sketch here, the green vector, right? And we can do this for all values of t's. So we can also go back in time if you want to know where the laser was 5 seconds ago. So we just plug in the value -5 in this case, and we get the position 5 seconds ago was OA minus 5 times AB, which is then the vector -22, -14. In this case, we can't draw this vector here on our graph because we don't have the whole coordinate system, but you get the point, right? The question we can ask ourselves now is, will the laser ever reach the point R at position 27, 14? And we can answer that question graphically, or we could answer that question graphically by just drawing the line of the laser in a larger coordinate system and then also drawing the point R. And if we do that, we will already see graphically that the laser will have actually never reached that point, it will miss it. Now the question is, can we also confirm that mathematically? And we can actually do this, and it's quite simple because we already know an expression for the position of the laser after t seconds, and this expression is given by starting position plus t times the direction vector. Now the question here is will the position ever become 7:14. That's what we have to answer the question. So in other words, we need to look whether we can find t so that this equation here is satisfied, right? And we can do that. So this is actually, these are two linear equations with unknown. So let's look at the top one, which is 27 equals 3 plus 5t. One linear equation with one unknown that we can solve now for t, and we get t is equal to 4.8. Now this means that after 4.8 seconds, the laser will reach the x-coordinate 27. And we need to check now whether it also reaches the correct y-coordinate, which should be 14 in this case. So all we have to do is plug in this value t into our position equation. And by doing that, we get that after 4.8 seconds, the laser will be at the position 27 and 15.5. So it's at the correct x-coordinate, but at the wrong y-coordinate. So if you would graph that position, it's given by this green position vector up here. So that's the position of the laser after 4.8 seconds. And you see we miss the red point here. Now let's take a second to appreciate what we did here. We described the line mathematically and we checked whether a point lies on the line or not. That's a big step. And now that we have answered that question, we can move forward. So far, we looked at the laser in the plane. And the question is, can we extend that concept into the space? So could we also describe a laser in space? And the answer is yes, of course. There's nothing that is holding us back here. So let's have a look at this situation here where we have a laser that moves on this straight line here through the point A and B. Now, with space, it's a bit hard to sketch it, right? So in this case, it's only a sketch. It's not accurate or anything, but you get the point. So again, here in this case, we know that the laser at time 0 is at the point A, and after 1 second, it moves to the point B. Now we are in space. So again, we can describe the position of the vector after t seconds with a general formula. Like in the two-dimensional space, we had a starting position plus t times direction vector, and we can do the same in the three-dimensional space. So also here we have the starting position, which is at A, plus t times the direction vector, which is AB in this case. Right? And this gives us the equation of this line. Now, again, in summary, that's the general equation of this line that describes this line or the position of the laser in space mathematically. And we can then have a look at a couple of different questions. So if you want to know, for instance, at what position the laser will be at the time 0.75 seconds, then all we have to do is to plug in this value 0.75 into the equation, and we get the position of the laser at that time. We can also go back in time as before. If you want to know at which position the laser was 5 seconds ago, now we just plug in t minus 5 and we get the position of the laser 5 seconds ago. And that's two things. We can, or that's the first thing, we can determine position determine the position of the laser at certain points in time. But we can also answer the second question that we answered before, which is, does the laser reach a certain point? So for instance, here we are looking at the point R, now a point in space with an x, a y, and a z coordinate. And again, we want to know whether the laser reaches that point. So since we know an expression for the position of the laser, we just need to check whether it ever reaches this position, right? So we need to check whether there's some t so that this equation is satisfied. So looking at the top row again, and we could also look at the second row or the third row, it doesn't really matter, but we look at the top row and we get the equation minus 14 is equal to 6 minus 4t. That's an equation, a linear equation with one unknown t. We can solve for t in this case very easily, and we get t is equal to 5. This means after 5 seconds, the laser will have reached the x-coordinate minus 14, but we don't know whether it has reached the correct y and z coordinate in this case. So let's check this. So let's plug in t equals 5 into our equation for the position. And when we do this, so we get this expression here, and we can compute that, and we get the position of the laser after 5 seconds is given by the position vector minus 14, 27, and 17. And that's actually exactly the position vector of the point R. So the point R lies on the line of the laser. Yeah, so we have confirmed that mathematically. So let's take a second to appreciate what we learned in this exercise. First of all, you learned, and that's the most important point, you learned how you can describe a line in plane and space using vectors. So using a position vector and a direction vector pointing into the direction of the line. That's the first thing, and if you understood this, then you have actually understood the whole concept or the main idea of this topic, right? And the second thing is you already learned how you can check whether a certain point lies on a certain line.